So we're looking here at gravity, practice 3, problem 11.18, or 11.8, what did I say, 11.18? And if you didn't know, back in February of 2018, Elon Musk's company, SpaceX, they began to launch a number of satellite trains, just one satellite after the next, in low Earth orbit, also known as LEO, with an intention to eventually put enough of these satellites up into orbit to provide full Earth coverage for satellite internet. This is what is known as Starlink, and if you actually get a chance to look in the night sky and you get a star train kind of going over you, you just see like a bunch of little dots just bloop, 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 all tagged together moving across the sky. And astronomers are kind of worried about this because it might mess up some observations and kind of create enough space debris that we might not ever be able to get outside of Earth if we want to leave the planet and go somewhere else. But that's an issue for another day and kind of above our pay grade. What we're just trying to do here is if these satellites are orbiting the Earth in LEO, they're about 550 kilometers, we would like to know what is the orbital velocity of one of these satellites. And we've got our answer here of 7,580 meters per second, but let's see how we actually go about finding this. Well, one of the things we need to consider is that when we're going into, if we kind of draw a picture of the Earth here, circular orbit. We're going to pretend these are circular orbits around the Earth to make our math a little bit easier for us. Then we know that the force causing this centripetal motion here, this centripetal force causing this circular motion, is the force due to gravity. And what we can say here is that this force due to gravity is Gmm, so mass of the Earth and the mass of the satellite, over, in this case, this is r squared, and that has to be equal to ma. So F equals ma, this is the mass of the satellite, times a centripetal acceleration is v squared over r. And if we quickly get rid of the mass of the satellite, it doesn't matter if it's a tiny mass, a hot dog, an asteroid, whatever, and then we get rid of one of the radii being the radius from the center of our Earth, or whatever you're orbiting, out to your position. That leaves us with just the equation that v squared equals g times the mass of what you're orbiting over r. And if we want to get rid of that square right there, we can just take the root of both sides. So we get that the velocity is equal to the square root of g times the mass of whatever you're orbiting, in this case it's the Earth, divided by your orbital radius from the center of the Earth all the way out. So for our Starlink satellites, what we'll find is that their orbital velocity is going to equal the square root, and I'm going to put that in parentheses to the 1/2, but that's going to be g 6.67 times 10 to the negative 11, that's the gravitational constant, times the mass of the Earth, which is 5.97 times 10 to the 24th, and then divided by the orbital radius. Now this orbital radius is actually going to be the radius of the Earth, because we got to get out to from the center of the Earth out to the surface, plus the altitude. So it's going to be the radius of the Earth plus the 550 kilometers. And our radius of the Earth is 6.38 times 10 to the 6th, and then we need to add the 550 kilometers, so that's going to be plus, and if we kind of convert that, that's going to be 5.5 times 10 to the 5th in meters. And this is all to the 1/2 power, because that's the square root. And at this point, it's just calculator time, plug and chug. I'm going to do the 6.67 and the 5.97 first. 10 to the 11 times 5.97 times 10 to the 24th. That gives me 3.98 times 10 to the 14th. And then I'm going to divide by the sum of those two values in the denominator, 6.38 times 10 to the 6th plus 5.5 times 10 to the 5th. This gives me 574,60173, and then I take the square root of that giant number, and look, lo and behold, I get 7,580 meters per second, which is exactly what our answer was. Okay, so this is how we do an orbital velocity. We look at big G, the mass of whatever it is you're orbiting, and then the radius at which you're orbiting at, and we need to be careful because that, if you're orbiting a planet, would be the radius of the planet plus your altitude. So that entire thing there gives us an orbital velocity. We got it through centripetal forces, because that's what's kind of holding us in this orbit here. And that's it. That's a quick little derivation and solution to one of these type of problems. If you think SpaceX should be continuing to launch these satellites to give everybody, in theory, high-speed satellite internet worldwide, then yeah, say so and why that's the case. If you think that we need to keep the skies free of this kind of thing and that someone should step in and kind of remove these things, then let us know. So with that though, this problem is finished. Take it easy. Have a good one.